Welcome to the 37th Theoretical Physics Colloquium by Professor Zohreh Davoudi from the University of Maryland. She's an assistant professor of physics at the University of Maryland and a fellow of Riken Research Center. She received her PhD in 2014 at the Institute of Theoretical Physics, University of Washington, sorry. She was a postdoctoral scholar at the Center for Theoretical Physics of Massachusetts Institute of Technology between 2014 and 2017. And since 2017, she is an assistant professor at the University of Maryland. She received numerous awards and honors over these years. She is a Sloan Research Fellow. Since 2019, she received 2019 Early Career Award from the Department of Energy. In 2018, she received the Kenneth Wilson Award for Excellence in Lattice Field Theory with a quotation for the fundamental contributions to lattice field theory in a finite volume that are essential for performing lattice simulations of complex systems. In 2016, she was an invited participant at the Rising Star in Physics workshop at MIT. She also received a Kara Prize in Physics for Excellence in Scholastic Record and Professional Promise from the University of Washington in 2011. She's also very active in outreach, physics outreach, and participating in many well-advertised and well-received discussions, panels, TED Talks, and stuff like that. Her research interests include lattice gauge theory, quantum simulations, nuclear effective field theory, real-time dynamics of strongly interacting matter, analog computing simulations. And today she will be talking about atoms and ions as quantum simulators of quarks, gluons, and nuclei. And with that, I'll give the microphone to Zohreh.
Thanks very much, Igor, for the very nice introduction. I really appreciate it. It's quite a pleasure to be here in this virtual colloquium series. So thanks very much for the invitations. I'm happy to tell you about some recent developments in trying to take advantage of quantum simulators that use atomic physics to simulate complex quantum many-body systems. And in particular, what are the prospects of using the systems for simulating quarks, gluons, and nuclei from the perspective of fundamental interactions that govern these systems. So let's get started with this by saying that my background is, of course, in nuclear physics. And the goal, one of the biggest goals of nuclear physics, to be able to start from first principles. And by first principles, of course, we know that to be the underlying theory, which is a standard model, and be able to build up this rich structure of nuclear physics, and in particular, for example, the chart of nuclear isotopes, all the way to very heavy isotopes and maybe more exotic and neutron-rich environments, and eventually be able to also make predictions, for example, for phases of a strongly interacting matter in universe described by the theory of quantum chromodynamics, and maybe learn something about the densest form of matter in the interior of neutron stars, and so on. So these are the big questions that we have in mind. And of course, as I said, it would be ideal from the theoretical perspective to go all the way back to the standard model, and in particular, the theory of quantum chromodynamics, and be able to predict all these interesting phenomena in nuclear physics, starting from the quark and gluon degrees of freedom. I don't want to say too much about QCD. I'm sure many of us in this Zoom room are very familiar with the theory of QCD because of the nature of this colloquium series. But just to say that this is really the gauge theory that is augmented by several flavors of massive quarks. And at the heart of it is really a simple Lagrangian that describes the interactions of the quarks and gluons, as well as the interactions of the gluons among themselves. And now if you add to this QCD theory, also the theory of quantum electrodynamics, you're only dealing with very few input parameters to be able to simulate the full nuclear physics in principle, right? So if you fix the masses of the quarks, as well as the coupling constant of these two theories, the quantum electrodynamics and QCD, then you can fix these quantities by a few physical observables. And then after that, if you start simulating everything from these few parameters, everything else is a prediction. So that's a nice thing about the theory. Of course, it's very hard to do the simulations, but at the end of the day, it's a theory with a few input parameters. Why is it so hard to simulate this theory? Well, QCD is a confining theory. In particular, at low energies, we have the phenomenon of, at high energy, we have the phenomenon of asymptotic freedom. At low energies that are relevant to nuclear physics, we would need to solve the theory non-perturbatively. And that non-perturbative method is really what makes things a bit complicated and more complex compared to, for example, quantum electrodynamics. So what can we do at low energies? Well, we can start trying to think about more effective degrees of freedom at low energies. Of course, we know that at energies of relevance to nuclear physics, it is not quarks and gluons that are governing, that are sort of the dynamic degrees of freedom that we have to deal with. They are mostly hadrons, nucleons, and pions. So if we are able to systematically write down all the interactions consistent with symmetry and symmetry breaking patterns of QCD that are made of these hadronic contents, these hadronic fields, and then fix the coefficients of these interactions to a few observables that we measure in an experiment, then in principle, we should be able to systematically make predictions for low energy observables in the theory. Of course, the challenge would be that if you want to reach higher precision or go to higher energies, you need to include more and more interactions. And therefore, you need to fix the coefficients of these interactions, these low energy constants, by fitting to more experimental observables. And maybe potentially there are no experimental observables for certain quantities and certain interactions. And then we will be again in trouble, right? So that would be the challenge. Another path one can take is to think about solving the QCD itself exactly. So starting from the quark and gluon degrees of freedom, trying to reach to the hadronic and nuclear physics. And of course, this is the program that lattice QCD or lattice gauge theory offers. What it does, and I don't want to say too much detail about this, just saying that once we do lattice QCD, the degrees of freedom are still the quarks and gluons of the original theory. But now we discretize the theory such that the fields are presented locally on the sites or links of this lattice. And in order to fit this problem into a computer to numerically evaluate this theory, we have to discretize as well as truncate the space and time directions in the lattice. So of course, in order to get the physics right, in the end of the day, one has to extrapolate to infinite volume and zero lattice spacing. And this is a well-defined program. This is very systematic. And I see Mike Kurtz, one of the leading figures behind this program in this audience, which is a honor. So
thank you.
Of course. And then, yeah, so of course, then you have to use all sort of advancement in algorithmic and numerical methods to be able to solve lattice QCD, to perform calculations. So that's really the program. And the nice thing about that is that now, even if you don't have experimental quantities to fix, for example, the low energy coefficients of your effective field theories for certain quantities, then in principle, you can use lattice QCD to find the values of these quantities, kind of replacing the experiment, so that you can also use this lattice QCD program to support the effective field theory program. Why does it matter? Let me give you an example. And before that, I want to just say in one sentence that it is believed now that lattice QCD combined with these effective field theory methods is on track to deliver results on important quantities in nuclear and high energy physics. So it is not that you either use effective field theories or lattice QCD. Nowadays, we know that the path forward might actually be to combine the two and match the two to be able to reach to the quantities that we otherwise cannot reach with either of these methods. So what has been achieved? Well, a lot has been achieved, and it would be impossible to tell you about all these very exciting progress in this field of lattice gauge theory. From my perspective, because I'm very much interested in multi-nucleon system, the example that I've picked out of many other examples that I could have picked is this plot by the NPL-QCD collaboration. I'm part of this collaboration at the moment. I was not part of the collaboration at the time that this study was performed, so I cannot take credit for this nice work. But otherwise, let me tell you about it. The significance of this plot is that it shows that lattice gauge theory program has reached to the point after many decades of the hard work that it can actually predict the binding energies of nuclei out of the quark and gluon degrees of freedom. So you can start from the quark and gluons of QCD without making any assumptions about the fact that these bounded states of nucleons or even hyperons would arise from QCD, but they actually arise from the dynamics once you solve the QCD. One caveat in this picture is that the input parameters that I was talking about in the first slide are not set to the physical values of these parameters. And in fact, the masses of the quarks or the masses of the light quarks are being set to be equal to the mass of the strange quarks, so they are rather heavy. And therefore, this plot does not correspond to what you see in experiment. It is a nice and kind of intellectual question to ask, what would you see if you had unphysical quark masses in nature? Would you see nuclear physics? And in fact, this plot is hinting that yes, you can see these bound states of nucleons, but also the hypernuclei. So that's the significance of the plot, and we're more computational resources. We are moving towards being able to have the same plot and even more at the physical values of these quark masses. But just to tell you about the scale of these computations, this study itself took about 2 years and a few hundreds of millions of CPU hours on the largest supercomputers in the US. So this is kind of a significant calculation and tells you that really a huge amount of computational resources are required to reach the kind of advancement that we have seen in the field now and the kind of precision that we need to make progress in nuclear and high energy physics. So that we have to keep in mind. And maybe just one other highlight of this program, again, the work that I was involved with, is the fact that not only we can now get the light nuclei out of QCD, we can also look at their reaction properties. And a very important process is the proton-proton fusion, which is responsible for generating energy in stars such as sun. And we were able to, again, with the caveat of being at this heavy on physical quark masses for the moment, calculate the cross-section for this process directly from the quark and gluons of QCD. And in fact, with rather crude approximation, we can also get a handle on this short distance, highly uncertain low energy constant of the effective field theory that described the short distance two nucleon coupling to the axial current. If you're familiar with this term, this is called L1A. And already with our lattice QCD calculation, which is really the first and preliminary result, we can get a value for this coupling that has uncertainties comparable to the current phenomenological constraints. And of course, with more refined calculations and towards the physical values of the quark masses, eventually, hopefully, we will be able to provide even more precision on this important low energy constant that can then fit into the solar models and refine those models as well. So that's the goal. So going back to this plot of being able to do more, starting from first principles QCD calculation, really what the path might look like for us, given the cost involved in this calculation, is that presumably and hopefully in the next few years to up to a decade, we would be able to precisely calculate quantities in the few nucleon sector, this light nuclear sector of QCD, and maybe hypernuclear sector as well. And then with the use of effective field theories, then you can match to the larger isotopes. And in particular, as I said, this effective field theory program is very important because when it's matched to QCD, it can then become the basis or the input into many-body nuclear calculations that are using all sorts of methods from ab initio to more kind of phenomenological or macroscopic way of calculating, but in a sense kind of systematically match all the way from QCD to these larger isotopes. This is really a multi-step and long program, and that's sort of the dream of the community, to be able to make everything more systematic and reliable in terms of connecting to the underlying theory. And in fact, this program has already started, just showing a very small plot over here, saying that already the physicists in the nuclear many-body ab initio community have taken this results of lattice QCD calculations in light nuclear system and have therefore fixed these low energy constants of the effective field theories and use those effective field theories to make predictions for systems for which lattice QCD cannot yet make any predictions for. And in particular, for example, in this case, at these heavy point masses corresponding to the calculations that I just showed, they can make predictions for what the binding energies of something like lithium 5 or 6 would look like. These are the systems that we cannot calculate with current computational resources with QCD, but using this matching program, we can go all the way to these larger isotopes. And even there are works that look at this for oxygen-16 and things like that. So this is exciting, but this is just a starting, and hopefully is going to advance and improve in the upcoming years. So that's where we are now. And in fact, I should just say that lattice QCD is really supporting a multi-billion-dollar experimental program. I just talked about a small aspect connecting to concerning nuclear physics, but in all branches of hadronic and high energy physics, lattice QCD program is important, and in particular, the topics that it covers from nuclear structure and astrophysics, hadron structure, hadron spectroscopy, as well as this program in fundamental symmetries and searches for new physics, lattice QCD is really playing a role. So I told you about this nice progress. I could have spent the whole colloquium on this, but because the colloquium is actually about something else and is about how we can go beyond these calculations, I want to mention a few of the challenges that we face in lattice QCD. So of course, we've made a lot of progress, and there's been so many successes, starting from just calculating the simple masses of the hadrons and so on, all the way to where we are, where we can actually simulate the nuclei. But there are challenges, and we don't think that in near future or even in far future, we would be able to simulate a large isotope itself without having to go through this sort of multi-level matching to effective field theories and ab initio methods. If you want to just do something like an isotope, I've shown radon, I think here, with hundreds of nucleons in this isotope, if you want to simulate this starting from QCD, that would be very hard. And the reason for that is basically multifold. One reason is that the complexity of the systems grows factorially with the number of quarks. When you start from the quark degrees of freedom to build your nuclear correlation functions in these lattice QCD calculations, then you have to deal with the factorial growth in the complexity because of this. There's another problem. There is a severe signal to noise degradation already in the nucleon correlation functions from lattice QCD. So at large times or Euclidean times, which is what we do, we see the dominance of noise over the signal, and it would be very hard to beat this. In principle, you need to increase exponentially your resources to be able to get the statistics that you need to extract your signal. And there's something deep about this, comes from nature of QCD and these light degrees of freedom that depends in the theory, but I don't want to go into that. Just keep in mind that as we try to simulate larger systems with more nucleons in them, then we have to deal with a very severe signal to noise issue that requires exponential growth in the resources to beat it. The other problem is the fact that we need very high precision to be able to resolve the nuclear energy levels. This is very different from a single nucleon physics, because as you gather more and more nucleons together, you start to see very small excitation energies in this nucleus of the order of just few kilo electron volts. And this is already orders of magnitude smaller than the masses of these heavy objects. So your calculation better be able to resolve orders of magnitudes of difference between, in the same calculations, orders of magnitudes of difference in energy scale between different excitations compared to the masses of these objects. So again, you need huge amount of resources as you increase the number of nucleons to include in your calculation. It's not just that signal to noise problem and things like that. There is even more severe problems that we have to deal with. If we want to, for example, think about getting the phase diagram of QCD directly from this lattice gauge theory program. And we are all familiar with this. There is a sign problem as soon as you introduce a chemical potential, and then because of the way that we do these calculations using Monte Carlo sampling methods with the path integral formulation, once we introduce the chemical potential, then we have to deal with an oscillatory weight for these Monte Carlo samplings, and that's basically not possible. It requires, again, exponential increase in the resources to resolve the signal. So again, we would be limited to really make predictions for this very interesting phase diagram and try to see whether all sorts of conjectures and hypotheses are correct. If you want to do this from the underlying theory, that would be very difficult with the current methods, it seems like. Another class of very interesting observables that we have not been able to look into because of our way of doing this conventional lattice field theory methods is the fact that our calculations are limited to Euclidean time. If we want to look at the real-time dynamics of matter, that would be very difficult. For certain quantities, we have been able to get around this problem. For example, if you're interested in 2-hadron or 3-hadron scattering amplitudes, there are clever ways to go about this problem by using the Euclidean time calculations to get the information about the Minkowski time amplitudes, but not in general. For example, if you're just interested in understanding how matter evolves after heavy ion collisions, how it hadronizes and thermalizes and so on, this is something that we have not been able to do with lattice gauge theory methods. And in general, a wealth of dynamical response functions, transport properties, distribution functions, and all sorts of non-equilibrium questions that you can ask about QCD, we unfortunately have not been able to explore, again, because we have been limited to this Monte Carlo sampling that becomes oscillatory in phase if you introduce the real time. And if you want to do Hamiltonian evolution instead of doing path integral formalism, again, there is kind of a sign problem still, because you have to deal with exponentially large Hilbert spaces if you think about the Hamiltonian evolution, and then do these oscillations, this oscillatory phase on the wave function of the system that is very complex. So what can we do? So of course, we've done so many nice things with lattice gauge theory, but of course, this is not everything that we would like to get out of it. So this is an opportunity to explore new paradigms and new technologies in simulation, I think. And this is what the community nowadays is excited about. And that's whether or not we can use quantum simulators and quantum simulation and quantum computing in general to change the way we actually perform lattice QCD calculations, to be able to look at dynamical properties and finite density systems and so on. So that's the goal of this sort of newly formed program. And now I want to sort of start talking about what this quantum simulation means and what these atomic simulators can do for nuclear physics and what the status of the field is with regard to that. But before that, are there any questions about this kind of long introductory part of the talk?
I don't think there were any questions that I've noticed up to this point. I did have maybe one comment, if I could use this moment then. You had some phrase saying something along the lines that lattice simulations were supporting multi-million-dollar experimental program. I think it's kind of sounding a little bit awkward in a way. Of course, lattice simulation is helpful to interpret the experimental data, but supporting it maybe a little bit is an overstatement.
So that's my choice of word, supporting. That's exactly what I mean. I mean, if you don't have lattice QCD to interpret, then your experiment is basically failed, right? What can you learn about the experiment if you don't have the theory to interpret it? Let me give an example, right? With regard to the fundamental symmetries program, a lot of times we need the strong interaction matrix elements because we're doing experiments with nuclei. Let me give examples: the dark matter detection experiments, the neutrino oscillation experiments, the EDM experiments, neutrinoless double beta decay. All these multi-billion-dollar experimental searches for new physics, if you don't know the nuclear matrix elements and the standard model contribution responsible, then how can you resolve the new physics contributions to these processes? G-2, another example, right? So really, I mean, we're starting to see that in order to sort of reach into that new physics era where we can interpret the results of experiments because of the wide use of nuclei and nuclear isotopes and hadrons in these experiments, we need this theoretical tool to be able to precisely and reliably, and without having to use all sorts of models with unquantifiable uncertainties, to be able to get these matrix elements and provide it to the larger community. So that's what I mean by that. Okay. All right, thanks. So let's start this discussion of quantum simulation. Well, what do we mean by quantum simulation? Well, this really amounts to leveraging a quantum system that can be controlled in an experiment to be able to simulate another quantum system that is more elusive, whether experimentally or computationally. So really broadly speaking, we are hoping to start from the quark and gluons, build the nucleons, which build the nucleus. But of course, we know that the nucleus is at the core of an atom. The atoms would build the molecules maybe build as materials, or in particular, quantum materials. And maybe in the end of the day, you can put everything together, make a large macroscopic system like the neutron star. And the idea of quantum simulation is to use the systems like atoms and molecules and these quantum materials, whether in a digital way or in an analog way, to simulate the properties of these systems that are fundamentally different, whether in terms of the degrees of freedom or in terms of the interactions, underlying interactions that govern them. And that's really the beauty of it. How can you use these fundamentally different systems to simulate the physics of the systems that are pretty much more complex, as we will see, either in a digital way, which would be quantum computing, or in an analog way, which is sort of finding clever ways to tune the interactions and degrees of freedom in these systems in such a way that they mimic the interactions in these more complex systems. That's the program. And of course, this is the right time to start thinking about this, because there is a range of quantum simulators with varying capacity and capability that is available out there, whether in companies or in universities, or nowadays even in national labs. And these are the systems that are based on various different architectures, whether condensed matter systems or atomic systems and so on. But it's kind of an exciting time to start thinking about what would happen to fundamental science, and in particular theoretical physics and computational physics, if we had access to large scale reliable systems that are built out of these quantum architectures. Of course, we're not there yet quite, but it's sort of starting to sound like we might someday have access to this system. This sounds very similar. I'm sure Mike would agree with me that 40 years ago, that was kind of the situation in lattice gauge theory. We didn't have access to large scale capable systems that we have today to do the kind of calculations we perform now. But at the time, we had to start developing the theory, the algorithm, the concept and everything to be able to actually use and take advantage of the computational systems that were becoming more and more powerful at the time. So we're kind of at the same stage. It might take a few decades to actually see the fruit of this program, but the idea is that hopefully we will get there. What we can do now to develop this program to something more interesting and productive as these systems get evolved. So these systems have been used in doing instances of simple models in condensed matter and in chemistry problems, but not so much yet for nuclear physics and high energy physics problem. Although the progress has started and there are very interesting and exciting work coming out, but I wanted to say that there are similarities with these condensed matter and chemistry problems, but there are major differences as well. So we have to keep in mind that differences when we talk to our colleagues that are doing quantum simulations for these other programs. And what are those differences? Well, if you just start from the nuclear Hamiltonian, forget about QCD and quark and gluon interactions, just the nuclear Hamiltonian itself might sound a bit more like quantum chemistry problems because you're dealing with interacting fermions, but the interactions are more complex because, first of all, we don't know the Hamiltonian itself with arbitrary accuracy. There are short, intermediate, and long-range interactions involved. There are 3 and multi-body interactions, and there are pions and other bosons that can exchange the nuclear force, and they can also become dynamical. So we're dealing with more degrees of freedom and more complex interactions compared to a quantum chemistry problem. The difference is even more major if you start from a standard model and try to simulate this nuclear hadronic systems, right? Of course, we are now dealing with quantum field theories, and in particular, we have both bosonic and fermionic degrees of freedom that are coupled and dynamical. And more importantly, they exhibit not only the global symmetries, but local gauge symmetries, right? This is something that you don't have to deal as much in this kind of non-relativistic quantum chemistry systems that people deal with. We have to take into account the relativistic feature and the fact that the particle number is not conserved. The vacuum itself is non-trivial, especially in the strong interacting theories. So these are all the features in relativistic quantum field theories, in particular in strong interacting systems like QCD, that we have to deal with that generally you don't have to deal with in a simple non-relativistic condensed matter quantum chemistry problem. And so how can we develop algorithms and theory and methods to simulate those systems? That's really the program. And in fact, this program has multiple different layers. I want to focus mostly on the simulations based on the quantum field theory. So basically this kind of the sector of the program, although there are very nice progress coming out of how to use these quantum computers and hopefully quantum analog simulators someday for simulating the problems based in nuclear Hamiltonian, so more effective field theory approach than just starting from QCD might be simpler. But for the talk today, I'm going to start from or focus on simulating based in quantum field theory. So this other part of the page. So the program itself is multi-pronged. It involves theory developments, algorithmic developments, as well as implementation and benchmark, because as I said, there are actually quantum hardware out there that you can get access to and test your algorithms, your proposals, and see how well they do, what are the limitations, what would be ideal for next generation hardware to be able to do your problem better. Because of all these different features that I talked about, this hardware might require different capability in terms of the architecture. And this is very similar to what we have seen in the lattice gauge theory program. The development of the clusters and supercomputers sometimes have actually followed the demand of the basic scientists, and in particular lattice gauge theories. So is that going to be the case in this program as well? I think that's probably the case, and we'll see how things develop. Let me give you a few examples of each of these, and then I start talking about the atomic quantum simulators. So as I said, you can already use these systems to do lattice gauge theory problems. The problems we can do are very small. You can solve them on a piece of paper. So it's not something that quantum computer can do for you that you cannot already do with your classical computational resources or even analytical methods. But that's a proof of principle that once you have bigger systems, you may be able to do what you cannot do today. And that's the point. And that's really the milestone for this field was this work by the group in Innsbruck in Europe, where they use this trapped ion 4-qubit digital quantum computer to simulate the dynamics of the Schwinger model. So Schwinger model is the one-dimensional, 1 + 1 dimensional quantum electrodynamics. And it has similar feature as QCD, such as the generation of these electron-positron pairs out of the strongly interacting vacuum. And in this case, they've looked at the dynamics of this vacuum and the generation of these pairs as a function of time. So this is a real-time dynamic calculation that the quantum computer has done for you. And this is really the dream, right? Once you have bigger and more reliable systems, maybe we can start to think about the simulating dynamics of QCD. It might be a long way to that point, but this is already the proof of principle where you can use the systems once they are bigger and more reliable. And there's been a lot more since then. There's been calculations of the dynamics of the Schwinger model on a different architecture. In this case, this is the superconducting circuits that can use can use them as qubits. This is from IBM, and these are the researchers at the University of Washington and Oak Ridge that did this dynamical properties of the system, as well as some static potential calculations and the Schwinger model. And in fact, at the University of Maryland, we're also performing real-time dynamics of both abelian and non-abelian lattice gauge theories and testing them on these trapped ion digital computers, and that are now more capable than what they were back then in 2016. So we really want to push the limit of what's possible today with the more advanced systems. So that's quite exciting. But that's not the end of the story. Really, we have to develop the theory because at the moment, the systems are small, so we don't run into much of the trouble. But once you actually want to do a big scale calculations and do something meaningful, then you start to see that your theory is not well developed to do such calculations. And I'll tell you an example of this. One example is thinking about simulating non-abelian lattice gauge theories. Okay, so again, I have a long equation here. I don't want to go into the detail of this. This is an equation for lattice gauge theory for the Hamiltonian formulation of lattice gauge theory that is done by Kogan and Susskind many years ago. And the formulation is based on splitting the fermionic lattices. So it's a lattice gauge theory still. And then you have this staggered fermions that are interacting with the gauge fields through this fermion hopping term. There is the fermionic mass term, and the energy of the color electric field and the energy of the color magnetic field are described by these two terms in the Hamiltonian. And in particular, there is this plaquette term in the Hamiltonian that is quite complex to actually implement in this Hamiltonian formulation, and it only appears when you have two-dimensional theories. But in any case, the important thing about this Hamiltonian formulation is that now you have to deal with local gauge symmetries, and in particular impose them by hand on the Hilbert space of this Hamiltonian. So if you start to naively build the Hamiltonian corresponding to the Hilbert space corresponding to this Hamiltonian, you actually end up with sectors that do not satisfy local gauge symmetries, and in particular Gauss's law. So this is the Gauss's law, and it's a local condition saying that the electric field, or non-abelian or abelian electric field, depending on your theory, should be balanced by the fermionic content at that site. That's the statement of the Gauss's law, which is a local constraint that you have to input on the states in your Hilbert space. So what it ends up being is that the full Hilbert space of the theory is basically redundant and unphysical. Only a very small sector of it would satisfy the Gauss's law corresponding to the eigenvalue 0 of this Gauss's law operator that I have there. And in fact, you might ask, well, what's the size of this Hilbert space compared to the rest of the Hilbert space? Well, we've done this exercise for SU2 gauge theory only in 1+1 dimension. And what we actually end up seeing is that the size of the Hilbert space grows exponentially with the size of the system. And that exponent itself actually grows logarithmically with the cutoff and the excitation of these electric fields. So you can imagine, and the physical sector of the theory, actually this exponent asymptotes to a constant value. So what you can imagine that even for a small system and for a small number of excitations in these gauge fields, you already see hundreds of orders of magnitude difference in the size of the physical sector of the theory and the size of the full Hilbert space. So we're talking about huge redundancy, right? Why does it matter? The reason it matters is that even if you start evolving your system from a physical state, because of the imperfections in your simulation, either because you're digitizing the simulations or because you have a quantum simulator that is not perfect and has all sorts of noise, then you start to actually bridge into this unphysical sector, which is huge. And you're going to lose coherence very quickly. So it's very important to actually start with formulations that have better starting point in terms of not having to deal with these redundancies. And again, this is just a slide that I want to show and not really go into the detail. You can look at this paper that we had recently to just look at the different formulations of this SU2 lattice gauge theory and try to find out what formulation might be more optimal for quantum simulation. And in fact, the formulation that starts with more gauge invariant degrees of freedom in the beginning to avoid this problem of huge redundancies in the Hilbert space actually performs much better in terms of the Hamiltonian simulation than the others. But if you're interested in the detail, you can look at this paper by Indrakshire Chaudhary and Jesse Stryker that actually developed this formulation, and see the details of that there. And there are so many other works really concerning how to make progress in this program with regard to this theory considerations. What about algorithmic developments? Well, these quantum simulations of quantum field theories really started by this milestone work by Jordan, Lee, and Preskill for showing what are the algorithmic requirements and quantum resource requirements for simulating a scattering in scalar field theories. And there has been more work to come up with more efficient basis states and formulations for the same problem that scales in certain conditions better than the others. There's also been a lot of work in, again, the Schwinger model, the one-dimensional quantum electrodynamics. And in particular, the work that I want to highlight is this work by Alex Shaw and collaborators in 2020, where they did a very nice comprehensive study of the efficient quantum algorithms for the Schwinger model, and then told us that if you're interested in certain precision and accuracy on dynamical quantities of certain quantities, what are the number of entangling gates in these digital computations in the near term? And what are the number of T-gates? So these are the gates that are more kind of expensive in the far-term applications that are quantum error corrected. And you see that the requirements are very huge. We are talking about hundreds of thousands of gate implementations. And at the moment, we can only do tens of these gate operations because of the coherence time of the systems. So we need orders of magnitude improvement in resources to even start seeing precision in simulations of Schwinger model. But let's not get discouraged. Let's just try to actually find out what is required. And this is what we need to do for QCD. Yes.
Zohreh, we have a question.
Sure.
3, you have a question?
Hi, Zohreh.
Oh, hi, Zohreh. How are you?
I'm fine. How are you?
Good.
Yeah, so I have a question, which is that you were showing 1+1D simulations, and they've been very successful. I wanted to know, what is the state of the art in 2+1D? What kind of gauge theories can you simulate?
Yes, a very good question, Sherry. So 2+1 dimension, there has not been any implementation besides one single paper by Martin Savage and collaborators last year, which was basically a few plaquettes in SU2. So that's in terms of the implementation. In terms of algorithmic and theoretical developments, there's been quite a lot of work, but I would say that until we actually have efficient implementations, it's hard to say what's best compared to the others. The papers that I can actually point you to are these ones. So these are some references here for progress in 2+1 dimensional U1 gauge theory. There are a few papers on SU2, but what I can say is that this formulation that Jesse and Indrakshi have developed, the loop string hadron formulation, can be generalized, and it has been generalized to higher dimension without having to deal with much complexities of the other formulations. Because of a simple trick, you can actually show that you have to deal with only one-dimensional abelian constraints in any dimension, even if you're interested in something like plaquettes and things like that. So again, if you're interested, just take a look at this and we can talk more afterwards.
Okay. All right. Thanks. Yeah.
Thanks. All right. So now the question is, as I said, can we as the theorist impact the developments in the hardware? And in particular, what are the hardware requirements for the simulations that we are interested in given their complexity? So the main topic of this talk that I think I'm pretty much, I don't have enough time to go through this whole aspect of the talk, but we'll see how much I can cover, is the fact that maybe we can also use these atomic simulators, whether in the form of cold atom systems or trapped ion systems, to simulate lattice gauge theories and maybe also this effective field theories of nuclei. So for that, we have to understand what these systems are able to do at the moment, and what they need to do, and what capabilities they have to introduce in near term to be able to be more effective and more useful for the type of simulations we have in mind. So I'm going to start with the ions. So the trapped ion systems are basically a bunch of ions that you put in a harmonic trap. And this confining trap, you can align these ions in a single line because you have more confinement in the transverse direction than the axial direction. And then you start to manipulate these ions with these very focused lasers, right? So these, then there's interactions between the ions and atoms can in principle be engineered to simulate the interactions of your target system. So that's the idea. Because of the time, I don't go into the details of the ion laser Hamiltonian. There are certain interactions that exist there. So let me not give a lot of details of this. But really, the general idea here is that you have this chain of ions. They're ions, so they have charge. So not only they see this common confining potential, they also have the long-range Coulomb interactions between them. So now if you solve the equations of motions for this chain of ions, you see a bunch of normal modes that are common to the whole system. And because these normal modes basically are shared by all the ions, you can use them as degrees of freedom that are helping you to entangle the different ions in your chain, right? So if it's very similar to sort of this idea of having two ions that are emitting sort of these virtual phonons. So if they're exchanging a virtual phonon, they're basically effectively coupled or entangled in this language. So you can use these normal modes of motions to entangle the ions. And this is really the picture that, if you're familiar with this term of Molmer-Sorenson entangling gates, which is really the important operation in a quantum system, because that allows you to impose quantum entanglement, which is really the powerful way of doing the quantum. This is really where the power of a quantum computer is. And the way you actually do this is by virtually exciting the phonon modes. And as a result of that, couple the two, for example, a spin down and a spin up systems along the chain. And this basically entangles or creates a highly entangled state between the two spins. So again, this is a lot of detail that I cannot go into, but basically by using the correct set of parameters of this Rabi frequency of your lasers and the detuning of the laser from these sideband frequencies, you can end up having coherent oscillations between a spin up and down, for example. So that effectively basically couples these two and avoids this sort of single ion transitions of this form. So this is sort of really the physics behind this entangling gates in the trapped ion system. But you can also do something more analog with these systems. If you have this chain of the ions sitting along the z directions, and you introduce two sets of counter-propagating global Raman beams to address these ions, then you don't have sort of individual control over the ions because these are global beams. But nonetheless, you can still use this system as an analog simulator for a quantum spin Ising model. Because you can show that the effective Hamiltonian of the system has a form of sigma x type interactions, all-to-all interactions, where this coupling Jij actually goes like power law, 1 over I minus j to some power. So it's an interesting spin systems with long-range interaction. And in particular, now you can do interesting things like this dynamical phase transition for 53 spins that was done in this paper by Chris Monroe's group in Maryland, where they look at the dynamics of the spin systems after quench. And they do this for a system where you can start to not be able to use this classical simulation methods to be able to simulate a dynamical property like this. And therefore, this is really already at the verge of using quantum simulators to do problems where classical simulators cannot do. So that's very interesting. I have another example here that I'm gonna skip, but if you're interested, ask me about this later. This is an example of a spin system that shows the confinement. And in particular, again, in Chris Monroe's lab, they're able to look at this domain walls of a spin systems that have the confinement property, just like QCD, and then look at the dynamical properties after the quench in a system that has this confinement property and see very interesting features. So you can imagine maybe someday using these prototypes of QCD, these spin systems, to learn something about confinement and dynamical phase transitions and so on in the context of QCD. These systems can be used as a digital quantum computer as well. So how does it work? Now, instead of having just two sets of counter-propagating global beams, I can introduce this individual laser beams. I cannot, but my experimentalist friends can. And this is, in fact, a very interesting technology of the past few years where you can have the individual control over the ions. So you can separately manipulate them. And therefore, this system can be used as a digital quantum computers, interestingly. So what does that mean? In a digital computer, you just tell your experimental friend or the company that this is the quantum circuit that represents the time evolution of my Hamiltonian or whatever quantity I'm interested in terms of a universal set of gates. Then just with that circuit, the experimentalist or the practitioner starts to turn that into the intrinsic gate sets of these, for example, trapped ion systems, these Molmer-Sorensen gates and so on. And then there is sort of a stack of operations that are involved. And in the end of the day, with highly efficient and high fidelity state preparation measurements, you end up getting the results that you want, right? And in fact, there are many, many examples of this. Again, I gave you the example of Schwinger model in the beginning, was kind of an example of the digital quantum simulator. And this is an example of finding the ground state energy of the deuteron using the ion trap quantum computer in Maryland, which you can find in this paper. So that's quite interesting. You can already start these systems to look at more non-trivial problems that were possible before. Again, I have another example of finding the ground state in the Schwinger model with a 20-ion analog quantum simulator that performs in sort of an analog digital sense. But again, because of the time, let me not go into the details of this. Look at these publications or ask me later how this works. But this is just to show you that there are so many developments in using these systems to look at problems that are of interest to us in nuclear and high energy physics already. Small problems, but let's not get discouraged and see what we can do as these systems get more developed. Another thing that kind of relates to what I have been doing in the past couple of years with my experimental friends is to how to make these systems even more advanced and use this analog simulation mode to simulate the theories that are complex, like lattice gauge theories and so on. Because what I told you about this analog simulator in the beginning was that you have two sets of global beams and you can just simulate an Ising model, right? So that's not quite enough. This is not what we're interested in terms of lattice gauge theories. We need more complex interactions. So one extension of what you can do before, which we presented in this paper, is to enhance the capabilities of this analog simulator by not only introducing the individual addressing and control, but also to increase the number of global beams with very specific configurations. This is important because you want to optimize the interactions that you get without having to introduce any unwanted or mixed interactions. And that's really the trick. That's really what the complexity is, to work it out in such a way that you end up with an effective Hamiltonian that represents the theory that you'd like to simulate. And in particular case, we can actually end up with an Heisenberg Hamiltonian, a spin Hamiltonian, where not only you have the sigma XX type interactions, but also sigma YY interactions and sigma ZZ interactions with the couplings that can be tuned independently, freely compared to each other. So that's a very enhanced capability that the analog simulators didn't have. And these systems are now starting to being built based on this theory proposal. So that's the exciting part. So why do we care about an effective Hamiltonian that looks like the Heisenberg model? But turned out that there are certain classes of lattice gauge theories that can be represented with an Heisenberg spin Hamiltonian. Well, maybe not too surprising. The Schwinger model is one example. With open boundary condition, you can turn the Schwinger model Hamiltonian to a spin Hamiltonian that is actually a Heisenberg chain with the ZZ interactions that are like long range, all-to-all interactions. So that's one example of it. And in fact, we can do a classical optimization problem to find the laser properties. These are Rabi frequencies and laser detunings in these analog simulators to simulate both the nearest neighbor and the long-range Coulomb interactions in the Schwinger model. So that's quite exciting. You can also look at other gauge theories. For example, Chern-Simons theory in 2 + 1 dimension is another example. Z2 theory in 2 + 1 dimension is another example. Again, even though these are two-dimensional theories, you can map them to a one-dimensional chain of ions and use this optimization program to be able to find exactly the couplings that you need between the different spins in this case that represent your field theory. So that's interesting. So there are some capabilities here, and we're excited about that. But of course, we cannot represent all gauge theories of interest in terms of these simple spin-to-spin interactions. And in particular, QCD itself, of course, is much more complex. Also the nuclear Hamiltonian, right? So the big question is, can we expand this trapped ion toolkit to further advance the capabilities of the quantum simulators for problem in nuclear and high energy physics? And I can give you very quickly two directions that we're exploring. One is to engineer more complex spin interactions, the detail of which unfortunately cannot say much because of the time. But basically the idea is to generalize these Mollmer-Sorenson entangling type interactions to entangle more than 2 spins at the time. So entangle 3 spins or 4 spins with certain interaction patterns that we have the ability to engineer and tune. So let me go through this. So basically the hope is that you can do the 3 spin down and up, couplings and so on, and that can be tuned. And this is a direction that seems promising, and we've actually made a bit of progress in actually making it work for certain gauge theories. Another very interesting direction is to actually leverage the phonon modes for simulating gauge theories. Of course, the gauge degrees of freedoms are bosons, and we already have these phonon modes that are bosons in a trapped ion system. Why can't we just map the two instead of having to do something more complicated, right? So there are ideas out there of how to do this. The phonon modes are global, so we have to make them local because we're dealing with local gauge degrees of freedom, of course. And this can be done. You can use the microtrap technology that is now quite being developed out there in experiments, or you can use other new ideas like this tweezers that pin the ions at certain locations. So they only have this local phonon modes of motion as opposed to having this kind of more global modes. So there are these technologies that are out there. And in fact, experiments are now starting to manipulate the phonons in the same way that they manipulate the spins or the ions themselves. So that's quite exciting given this experimental capability. And again, we've made quite a bit of progress of simulating certain lattice gauge theories that have this have this bosonic modes by mapping them to the phonon modes of the theory. So stay tuned. So Igor, sorry, I know that I've talked for almost an hour. And do I have another maybe 5 minutes, or should I stop here?
Absolutely,
Okay.
No problem.
Sorry about that. Yeah, I mean, this part I really go quickly because the title of my talk was Atoms and Ions, and it seems like I didn't give too much credit to the atomic cold atom physicists that have made a lot of progress here. So let me just say a few words about what we can do with the atomic systems as opposed to these trapped ion systems. Now, this cold atom systems in optical lattices, sort of, this is a nice graphic of that, and have a simple physics, in fact, right? they can, these are artificial crystals where you use these laser beams to artificially form these crystals, where you can actually now put the species of the atoms at the wells of these potentials, right? So you use these laser beams to basically create these crystals of the atoms. The nice thing about this is that you can trap fermions, you can trap bosons, you can trap mixtures of fermions and bosons. So this is very nice, right? And in particular, in trapped ion systems that I talked about, we have spin degrees of freedom. We don't have fermions. And mapping the fermions to spins can become complicated in higher dimensions, right? But once you have the exact fermionic degrees of freedom or bosonic degrees of freedom, the mapping to the original theory in terms of fermions and bosons is much easier. So in principle, these are more natural quantum simulators than a trapped ion system is. A trapped ion system is a better digital computers than these other cold atom systems. So, but still, you can use them for both purposes, analog and digital, as they are being developed more into the future. And the effective microscopic Hamiltonian for these systems, generally it's sort of a Hubbard model, whether Bose-Hubbard model or Fermi-Hubbard model or mixture Bose-Fermi-Hubbard model. And it's basically a hopping term because the fermions or bosons, they can hop between these wells of these potential. There is the sort of a local interactions, density operations, and there could be chemical potential. But this is really kind of a simplifications because you can engineer more complex Hamiltonians just by using the different types of the potential. Maybe you have the super lattices and so on and so forth. But then more interesting technology is actually the Rydberg atoms in optical tweezers. And these Rydberg atoms in optical tweezers, the property that they have compared to this usual picture that I've shown here is that now you can also have the individual control over these because of these optical tweezers. So it's kind of the same system, but you're making these optical potentials in a more controlled way using trapping these ions, these atoms individually. So it's quite interesting. What's the status of the field? Well, I showed examples of the trapped ion spin simulations. Let me show you an example of cold atom spin simulations. In this case, these are Rydberg atoms. And in particular, in Harvard University, they've looked at the dynamics after the quench of a chain of 51 ions in a quantum simulator, where they start the system in this Rydberg state. They adiabatically evolve it, but at some point they quench the coupling to 0. And then they start to see these very interesting oscillations between domain walls of the Rydberg ground state or the excited states. Which is interesting. And there are some very rich quantum many-body physics in here in terms of the thermalization and the oscillations of these correlations and so on. I refer you to this paper for that. I'm just showing this to tell you again that these quantum simulators are doing a problem is actually reaching the limits of the classical simulations. And in fact, you can do a 51 ion sort of time evolution after the quench for this dynamics of these domain walls, which is really comparable to what you can do with this matrix product states methods, classical methods. What about gauge theories? Still the progress is exciting. Last year, there was this very interesting work from Europe on simulating a 71-site Bose-Hubbard model that actually simulates the quantum link model representation of the Schwinger model. It represents gauge invariance. And again, I can't go into the detail of this. This is really the interesting engineering of these optical potentials in such a way that the dynamic is really constrained to the gauge invariant sector. And this is sort of a proof of that. In experiment, the gauge violations or the Gauss's law violation remains pretty small as they do the time evolution of this 71-site theory Schwinger model with this analog simulator. So this is quite exciting. What about two-dimensional theories and non-abelian theories? Well, the progress has been a little bit slow but steady. There are very nice proposals out there, and they are becoming more practical. Here, you have to deal with the gauge links and the plaquette term. The electric field term, depending on your basis of states, could be trivial. A nice proposal many years back comes from, again, Europe, when they used this optical potential and used the kind of the dynamics of these species, atomic species, and their scattering in such a way that they have gauge invariance. And in particular, they pick the atoms in such a way that they have angular momentum conservation. And that corresponds to actually local gauge invariance in the system. This has not been implemented yet. This is just a proposal, but there has been many more proposals since then. And in particular, again, Indrakshi Rachadhari and the collaborator in my group last year had also an interesting proposal for the SU2 gauge theory in 1+1 dimension. If you're interested, check out that reference as well. And let me skip this because this was an example of what we can do with these quantum simulators now for nuclear Hamiltonian as opposed to QCD. Again, this is very challenging, but there are some ideas out there that one can start to explore. And let me just summarize by saying that, of course, we're interested in very big questions in nuclear physics. All of us in this room have one question or more that can pick in here that is very much interested in and would like to actually get a handle on from rigorous theoretical frameworks. And I kind of started my talk by convincing you that if you want to start from a standard model or QCD, one way forward is to to obtain the few body observables, interactions, matrix elements, amplitudes directly from QCD, then maybe match them to quantum field theories in the few body sector. And then the quantum many body people can actually use these effective field theories constrained to either experiment or QCD to make predictions, hopefully, for the questions of importance in nuclear physics. But then in the rest of my talk, I try to convince you that now there's an exciting program in quantum simulation and quantum computation that maybe, hopefully, and maybe I can simplify this plot by saying that you can either start from QCD someday and use these quantum simulators to reach the physics that you're interested in, or maybe in another path, you can actually use these quantum simulators and quantum computers to solve the quantum many-body problem that starts from nuclear Hamiltonian to get to the physics. Either of these paths, again, we might actually need to enhance our simulation technologies with quantum computing and quantum simulation. And I tried in part of my talk to convince you that maybe these atomic quantum simulators are the way to go, at least in near term, or who knows, maybe also in the far term, these analog simulators would provide more advantage over the digital quantum computers. We have to see and we have to investigate. But nonetheless, this is very exciting. And in the end, many thanks to my collaborators in Lattice QCD. This is within the MPL QCD collaborations, as well as my collaborators in projects in Lattice in quantum simulations. And these are people that are actually coming from many different disciplines, if you've noticed. And not only nuclear physicists, but AMO scientists and QIS and computer scientists are very much interested in the problems that we care about, and hopefully with their help and their expertise and with our kind of perspective into these problems and understanding the complexities, we can work together to make this program work. Thank you very much.
Well, thank you. Thank you very much for a nice presentation.
Sorry for running out of time.
It's okay. We have some questions, and thumbs up. So the first question, René Bauwit, go ahead.
Yeah, hi, sorry. Thank you very much for this talk. It was very nice and very comprehensive. I have kind of a general question, and maybe it comes across as a little critical, but let me see whether I can formulate it properly. And I think it relates to quantum simulations in the end. But let me give you as an example what you've showed us first about lattice QCD. So you're taking a very, very complex many-body system, and you're trying to find particular features of it. For example, binding energies or excitation energies, which is very important to us if you want to extend the nuclear chart, as you said. Now, if you take the wrong pion mass, the wrong quark mass, you get the wrong result. And we know that. But it always gets presented to us as a proof of principle. The question for me, also with the quantum simulations, is whether at some point a proof of principle is not enough anymore because of the complexity of the system. If you try to get the right result, you will fail. So for example, you know, the wrong quark mass calculation is almost a decade old now. We haven't seen the right quark mass calculation yet. Because of the complexity, it's very difficult to achieve with the resources that we have. So at some point, the resources might be the limiting factor to achieve anything. And you've shown so many different examples in quantum simulations. To some degree, we have to figure out which of those are actually leading to an achievable results and which of them are just nice proof of principles that in the end will lead to nothing. So my question is really, which of these low energy nuclear physics calculations can be achievable over the next period of time and will not just be, you know, dreams or proofs of principles that don't lead us to anything in the end?
So that's a very good question. I think this is really the question that we should all ask ourselves in the beginning of this quantum simulation program. What are the observables that are easier and more promising to get something out in terms of gaining more insight, being able to really impact our understanding of a topic that we don't have good understanding of, and not really focus on the problems that even if we wait for another 50 years, we might not have the enough resources for it. I mean, the example of lattice QCD is correct, but I should say that in lattice QCD, it's a bit less dramatic than that, right? I mean, we have now this understanding that we will not be able to give you the properties of maybe carbon-12 with precision with the current methods, right? That's the understanding. Maybe if you talked to some people 10 years ago, it would have been a different answer. And that's why we came to the realization that we have to see what we can do in the few body sector with precision, and then leave the rest of the problems to the people that have better, more optimized methods to deal with these problems. We have done 800 MeV calculations. We have done 450 MeV calculations in terms of the pion mass. And other collaborations are now performing calculations of the physical pion mass. We haven't seen any good statistics out of them yet, but that doesn't mean that we are not going to see them. So this is just a matter of resources, really. I mean, these calculations are not taking a huge amount in terms of the fraction of the machines that are out there compared to many other fields. So I think it's kind of a bit overestimate that you've used a lot of resources and not produced what you need to produce at the physical point. I think this is doable for sure for the lattice QCD program in the next decade or so. We can do something in the few nucleon sector at the physical point. And the same way that we now have precision calculations for single hadron sector, right? I mean, these are the type of calculations that are impacting experiments already. And the hope is that in the few nucleon sector, we reach the same level of precision as in the single hadron sector. I think that's doable. That's not a dream that cannot be achieved. What cannot be achieved is the type of problems that I told you about. We understand this. We acknowledge the fact that we have limitations there. And that's why we think about quantum simulation. But again, I agree with you completely that it's important to know what's the rate of progress on the hardware development. And given that rate of progress and technological challenge, what are the best problems to focus on that we can get the answer to more quickly without sort of over spending ourselves on things that we might not get see the answer ever. We don't know, right? I mean, this is really tough, right? With classical computers, you kind of knew that the technology would sort of grow. There were, of course, very disruptive technologies that came along to allow the big machines that we have today. But it's kind of a bit different qualitatively in quantum simulation era, because even in terms of the type of materials and systems and so on, there is no consensus yet, right? There are trapped ion systems, there are circuit QD, there are superconducting qubits, all sort of technologies there. People are exploring to see what has the potential of being a scale up without having to kill the other good aspects of the current system. So we don't know, right? This program might completely fail. Hopefully that's not the case. But at the moment, the rate of progress compared to even 5 or 10 years ago would tell us that there are clever experimentalists out there that are really pushing the limits of what's possible. But it's very hard to extrapolate to the future. I completely agree with you, especially in the quantum simulation program.
Okay. Any other questions from the audience? I don't see any other raised hands. So actually, I wanted to ask one question that I had. When you were mentioning the limitations due to the sign problem in lattice QCD, is the quantum simulation going to be helpful to resolve this problem? And what exactly is the approach?
So there are two types of sign problems that we deal with in lattice QCD. One is in real-time dynamics, and one corresponds to the finite density, right? The finite chemical potential in the calculations. And the idea is that the quantum simulator can beat both. So the time evolution is more easier to kind of understand what's going on, right? Because in the end of the day, the Hamiltonian is what is naturally the Hamiltonian evolution. It is what's natural to a quantum simulator. You don't have to do anything extra, right, to be able to implement this. If you are given a quantum system, naturally it evolves through a Hamiltonian evolution operator, right, the unitary evolution operator. And because it has the full quantum mechanical wave function embedded into the qubits, and the quantum simulator keeps track of all the phases of the amplitudes as it evolves the system, we don't have to do any extra work to add up and subtract these phases and keep track of that cancellation. That requires a lot of resources, right? The quantum simulator is already doing that for you. The challenge in the end of the day is to how to extract the information that you want out of the final wave function, right? You have to perform a measurement. Measurement means that you have to collapse the wave function into a classical form. And you might run into a lot of problems because now you have a very big wave function that has exponential number of information or amplitudes in them. And now you have to collapse it into your classical memory and your classical resources, right? Again, there are many clever ways in the QIS community of how to deal with these large problems, and in particular, the measurements of large quantum many-body systems. What are the observables to look at from the local to global observables? What are the ways to avoid having to do an exponential amount of, putting exponential amount of resources to just do the measurement part, right? So I would say this is probably the most challenging aspect of this program, in particular for QCD considerations, right? This is really that part where thinking about experiments, everything hadronizes, comes to your detector, you detect them, you have to reconstruct what happened, right? Now we have the ability to actually stop the evolution at any stage we want and actually see the things that we cannot see in our experiment. We can just see the final stage in the hadronic form, but presumably we can see more once we stop the evolution and look at the wave function at that particular time. But then the challenge is how to extract the information you want, given this complicated encoding of your gauge theory into the qubits, and the amount of information that is stored in that wave function, what part of it is important for you, and how to extract that, right? These are the questions that require a lot of research, right? This is the start of a program, and this requires a lot of smart theorists and QCD physicists to think about. So I don't have the answer to that yet, but that's the hope. Just basically the idea that the quantum simulator can do unitary operations for you. That means that you don't have to deal with the sign problem, and the computer does it for you already, but then you have to deal with how to extract information that you're interested in from the final wave function of the system. For the chemical potential, it's the same thing. If you have a Hamiltonian that has the chemical potential, there is absolutely no difference between a Hamiltonian that has a chemical potential term in it or it doesn't. It's a Hamiltonian that gets evolved, and then you look at the final state. What is more challenging for a quantum computer is actually finite temperature as opposed to finite chemical potential. Why is that? It's very hard to prepare a thermal state on a quantum computer, again, because quantum computers do unitary operations. They do not do something that looks like e to the minus beta h, which is non-unitary. So you have to come up with ideas of how to represent a non-unitary operation in terms of unitary operations to prepare thermal states. There are ideas out there of maybe use your classical resources to prepare your thermal states, then represent that thermal state as your initial wave function and then start evolving it and so on. So these are interesting questions, like how to do the thermodynamics of this strong interacting theory. Again, it would be a very big research program if anyone is interested in getting into this. There are many open questions yet to be answered.
I see. Any other questions from the audience? Because I could have maybe a couple more, but I don't want to just take this over. Anybody else wants to ask questions? Okay, let me go then continue with the one that you were just trying to answer. And actually the follow-up was this. What you were talking about is, as I understand, is analog quantum simulations in the last answer. But I truly had in mind actually the digital algorithmic simulations of the sign problem using quantum simulations. Is there any progress in that direction?
So the answer that I gave applies to both. I mean, in the end of the day, the degrees of freedom are kind of discrete. Although there are ideas of using continuous variable quantum simulations to do problems, and I'm not an expert in those, but I can refer you to the people that think about along those lines. But in the end of the day, whatever simulators you pick, they have discrete sets of degrees of freedom. I mean, they have infinite degrees of freedom, but what are those degrees of freedom that you can control and prepare and manipulate and measure? Those are finite, right? Those are limited by your experimental capability. So this mapping of your problem to degrees of freedom is there for both digital and analog. In analog, you might have more freedom in your degrees of freedom. You might use the phonons, you might use the fermions and bosons on your cold atom optical lattices, right? But in the end of the day, there is a mapping that has to be done here, right? And because of that mapping, then you have to figure out how to interpret the wave function that you measure in the end of the process in terms of that mapping, right? Or in terms of the asymptotic states of the theory, which is different, right, in QCD. But in terms of avoiding the sign problem, it's the same thing. The only difference between an analog and digital simulator is that in one, the e to the minus iht operator, the time evolution operator, is being implemented continuously without being broken down to separate times. In a digital quantum computers, it has to get separated because otherwise it's very difficult to express it in terms of universal set of gates. So there is an error corresponding to digitization of the time evolution operator that you would like to control. That's your systematic errors, and you would like to make it smaller and smaller by adding more and more time steps, which means basically more gates. But that's the only difference. Like from the perspective of this concept of avoiding the sign problem, you're doing a unitary time evolution, either in form of a continuous time evolution or in form of digitized time evolution.
Fair enough. Okay, I don't see any other questions, so I would like to use this opportunity to thank you again for a nice presentation. And with that, we are done.
Thanks very much. It was very fun. And I apologize again for going over time. I hope that was okay for